Today's seminar is going to be given by Natividad from Cerezo, who comes from the Complutense University, from the Farmacia department. And she's going to talk to us about tissue engineering for ligament and bone regeneration. She spent 2 years in Australia and she got the degree, the chemistry degree here at Autónoma University, and the master degree. So it's going to be very good, very interesting talk.
Hello, everyone, and thank you for inviting me. I'm very glad to be here because, well, I did my degree here and my master, so this is a bit like coming back home. I'm working in the Complutense right now, but still I feel very happy to be here. As he said, I'm gonna talk about tissue engineering for ligament and bone regeneration. This is applicable to more kind of tissues, and we can discuss about it later. But first of all, I'm going to introduce myself a bit longer. As I said, I did a degree in chemistry and a master in material science. It was applied chemistry, but I specialize in material science and then I did my PhD in Complutense, and it was focused in biomaterial. I really like this topic. I've never heard about it before, and I'm passionate about it right now. During my PhD, I did a few exchanges in different labs, and the last one was in Queensland University of Technology in Australia, and that opened my next step to go for my postdoc. Then I went to Australia for my postdoc at the University of Queensland, where I collaborated with different universities and different schools. And then I came back to Spain with a Juan de la Cierva de Formación to the SSIC. And then right now I'm an assistant professor at Universidad Complutense de Madrid. Here, some of the places I've been working with or having collaboration. This is very important while you're going with your scientific career. Collaborations are very important. And just how I started with this project. First of all, I'm gonna do a small introduction, and I'm gonna tell you how everything came to do this project. So first of all, I want to explain what is tissue regeneration and what is tissue engineering, because like we sometimes change the topics and it's not exactly the same. So first of all, I want to clarify that. Then I'm going to speak about ligament regeneration, and I'm going to explain a particular case that is what my research will focus on. And then I'm going to go for bone regeneration, which is something that I'm doing right now and I was doing during my PhD. Well, it is about science, but it's also about money. Because like with the aging of the population, our tissues are aging as well, and they lose their application in our body. So we have like the bones that have to support our structure, but with the time they degrade and they don't work as good as before. And as we are getting older, and we are getting much older with the years, we have to fix our tissues, and this is where tissue engineering comes, but also it's a huge market in terms of money. So the research and the products in the markets right now are about 16.5%, but it's supposed to be in about 10 years, more than 50%. So it's worth it to do research in this topic. And it's important to mention that one of the tools that we are using a lot in tissue engineering is 3D printing. We cannot think about the tissue engineering without thinking in this technique. It's a very good approach because it's allowed to do many things. I have put two different kinds of tissue of 3D printing here, and we see one that is a very usual one is fused deposition modeling, which is cheap. We can get free softwares, but it's a bit less reproducible when we want to do small pieces. And it's just mostly focused on polymers. We can print this mostly polymers. This is about 1,000 euros. Everyone can have one, more or less, if you save a bit of money. Then we have this other technique that is robocasting. This one is also, oh, sorry, I didn't mention, but both techniques are layer by layer. So you put one layer, then you create an extractor that you can design before. But in this technique in robocasting is very expensive. This printer is 1,000 euros. This one is 100,000 euros. But with this one, you can print many different kind of things. You can print, for example, composite, not just commercial polymers, and it's very reproducible. When you want to translate a product to the market, it's better to try this one. But with this one, you can get very good things though. So now that we are a bit familiar with 3D printing, I would like to go to the tissue. Our focus is regenerate or replace or just cure something that is damaged, a tissue that is damaged in our body. And there is a few now you can find researching many different kind of tissues. And I have chosen those ones are the most usual, especially ligament, tendon, muscle, cartilage, and blood vessels, and skin, their soft tissue, and bone, which is a hard tissue. And I like bone because I'm a chemist, as I mentioned, and when you start in tissue engineering, what most of the chemists start in tissue engineering is through bone, because it has an inorganic part. We will talk about it later. The main objective I have after we finish this talk, I would like you to understand what is regenerative medicine and what is tissue engineering. So regenerative medicine places more emphasis in the use of stem cells. It's like we have the cells and we create tissue out of just the cells of the patient. However, tissue engineering usually involves biomaterials. So we can do more things. If you think about it, maybe you believe that tissue engineering, that regenerative medicine is better because, okay, we just need the cells, but it's not that easy. Here, I have placed just a small scheme. So we have a patient that has a defect in a tissue. We get the cells, we expand the cells, and we create little microspheroids. Then we create an intermediate. This is an example for cartilage. And then we get the tissue to grow, and then we implant it back. Do you think this is easy? Do you think that it's easy to create tissue? Well, unfortunately, no. Otherwise, we will do that, and that's it. But luckily, we have materials, and we can combine it. We can get the cells, create a scaffold by 3D printing, for example, and combine our material with the cells. And we can include growth factor, polymers, drugs to get not only a regeneration, but also to cure a possible disease. This is very interesting because sometimes we cannot regenerate the damage on a tissue. And sometimes cells are not going to be good enough to recreate a defect, but we can do what we call tissue engineering and just support medicine. So we are going to put an implant that is going to stay there, but it's going to help to maintain the properties of the tissue. Now that we know a bit more about tissue engineering, I'm going to speak about the ligament. Ligament is quite, in terms of composition and anatomy, is quite simple. It's a quite simple tissue. It's very similar to tendon. Actually, in the bibliography, you can find both of them very similar, and system has been used to regenerate both kinds. They're just fibrin collagens. Here you have the structure, because in terms of composition, it's not complicated, but it is in terms of structure. You combine, like, it's like just fibers of collagen that wraps itself. It creates a huge kind of rope that is the fiber of the ligament. And the cells that are actually part of this tissue are mostly fibroblasts. Something that we have to have in mind when we recreate, when we are like creating a tissue, when we are trying to create a new construct, we have to think about the blood supply. All our tissues are vascularized, and it's something we have to think about. And that's why we usually create constructs that are porous, because we need the blood vessels to go through, and then cells can grow and they can have nutrients. So in this, regarding tendon and ligament, there is two main products that are non-absorbable. So we're not gonna just regenerate the tissue. We're gonna put an implant to maintain, to restore the properties of the tendon and the ligament. And both of the polymers, more usual polymers, are polyethylene terephthalate, PET, and polypropylene, which are very usual, and we have it here, for example, and it's used right now in medicine, in tissue engineering. Now we're gonna start thinking, before I explain the project and everything I've done till now, just take a minute to think how many times do you use your hand during the day. We use it all the time. I'm using it all the time to express myself while talking. And imagine that something happened and you cannot move your hand anymore. Well, your life, you're not gonna die out of that, but your life is gonna be really worse. This happens when you have an injury in the scapulae interosseous ligament. I'm gonna speak about it a bit more right now. This is again talking a bit about myself. When I met Cedric back then, when was my supervisor in Australia, I came back, I finished my PhD here in Spain, and then he called me back. Nati, I got some funding, and I know you finished your PhD, and I was having a talk with my very good friend, Dr. Natividad, who is a surgeon, hand surgeon, and he's very worried. And because he's observing a lot of people that breaks a ligament in their hand, and they cannot restore what is happening in the hand. Like, the hand is never as good as before. I know you know a lot about 3D printing. I know you know a lot about, you know some things about 3D printing, you know about tissue engineering. Would you like to come and help me to create a construct and try to help people now that we have the expertise of a surgeon? I say yes, because I really wanted to go back to go back to Australia. But then I realized I didn't know anything about this tissue. So I started to read. I'm gonna let you think again, because we have a particular case. So they told me the scapulonoid ligament, where is it? First of all, I need to know what tissue is. Well, I know it's ligament. Where is the defect? It's in the hand. This is important because it's not gonna be the same a ligament in the hand than a ligament in the knee than in the mouth, for example. How is the structure? This is an interosseous ligament. It has something relevant. And what is the mechanical load? Obviously, the load that we are gonna support in our hand is not the same that we're gonna support in our knee, for example. So I started to read and we came from some ideas. I was lucky enough, and this is something I also want to mention, this, as you may know, this field is very multidisciplinary. I'm a chemist. I was working with a lot of biomedical engineers. I was working with this surgeon and material scientists. And I was lucky enough to meet Natalia Peroskinoska. Here's the reference. And she was a material scientist, an engineer, and she was very focused on the simulation. So she took a lot of data and she recreated a simulation of where is the scapulonoid ligament and what we have to do. With this help, I was able to work better in the lab. So this is the hand. Look, we have our hand here, and we have the scapulonoid and the ligament here. When you break this ligament, scaphoid and lunate just separate, and you cannot move your hand anymore as before. And this is a kind of injury that happens a lot in young people, because it's the typical one. For example, if you are if you do a sport, it's the typical one that when you fall, you just put your hand and it breaks. It's not super easy that it breaks. I don't want you to be worried, but when it happens, it's really bad. Then, with the help of Natalia, the help of Randy, the surgeon, I started to work in the lab, and Natalia was helping me a few simulations. So we proposed a geometry, and she was doing some simulation in the mechanical properties of the scaffold to check if that was good enough to tolerate the load that we were supposed to have in the hand. And then we did some 3D printing. We checked a bit the design, and then we did a few trials, and finally we came out with the perfect, with the best the composition of the structure. So we have two bonds here, and then we decided to create a bond ligament bond structure. Those bond plugs will be inside the bond. We will introduce this part in the bond, and it will be anchored, and then the ligament will be in the middle. So we will be able to restore the structure of the hand. After some of the simulation, we decided that 15 millimeters was a good length for the whole construct, where we have like 5 millimeters in the bone plugs. We will discuss about the structure a bit more later. And then in the ligament part length was 5 millimeters. And this is the polyethylene terephthalate, which is the polymer that we were using. As you see, it's quite hydrophobic. We will have to do something about it later. Well, but 3D printing is really nice, but it's also sometimes a bit annoying, because to optimize something, it looks great, like when you print in those YouTube videos, like a big structure, oh, it's super nice with PLA. Okay, try another polymer and try to do something really small and really porous. Things are not that funny anymore. And here we have like, I just checked the condition of the filament. This is an PET filament, just a commercial one. And I checked the condition, and they say, no, you can print it after 200, between 200, 210, even if you try a bit less. Okay, then I think, okay, for this that is very small, and I really want a structure, let's see what I get. I just checked 2 different temperatures, and look how different is the structure. If we increase just 5 degrees, the temperature of printing, we got a collapse in the struts in the middle, and this is not reproducible at all. So I was very happy I did this trial, because otherwise I wouldn't have been able to keep working with this polymer. And then I moved to 200 degrees. And then here, you see how this is better? It looks more organized, and the struts are not collapsing as much, but also the speed is very important. And for these small constructs, everything is really important, all the conditions. So when you print very slow, you see how the filament is flowing, and is very slow that the struts just fall and they collapse between them. So I'm not interested in this, because I cannot control this. I cannot go to a surgeon and tell, oh, put this, and the next week I print something and it's completely different. I need to have something very reproducible. So those two looks much better. I was happy. I print so many scaffolds, and we got good printing. But I needed to check about their mechanical properties, because if they're not good enough, they don't have a good load, maybe I cannot use them. So how did I do that? We are working in the body. We are thinking in a physiological condition. So I need to work in wet conditions. I measure the mechanical properties in this tank full of PBS, which is a phosphate buffer saline. And I place the scaffold between those two grips, and then I just put some load to separate them. And look, it breaks. It was quite flexible, not too bad. And then I organized all the data with the help of Natalia too. And we realized how the mechanical properties were really great for the tissue. So the ligament in the body, we are in the same range, even a bit higher. And then we saw how 200 and 450 and 200 and 600 in terms of mechanical properties were similar. So I optimized the condition to 600 millimeters per second speed of printing and 200 liters. After I did the optimization, I print the scaffold, which is quite nice, I think. And we got this organized structure. And look, now I included the bone plugs. This is gonna be inside the bone. Regarding the porosity, as I say, I need the cell to grow through on the surface, like to colonize the scaffold. Otherwise, this is gonna be rejected by the body. So I studied the porosity by microcity, and I observed how I have more than 50% of porosity in both here in the bone part and in the ligament part even more. So I'm happy because the cells will grow through and they will colonize the whole scaffold, I hope. But I have another disadvantage here because this, as I mentioned, PET is very hydrophobic. I need to increase the hydrophilicity. How did I do that? I just put some plasma treatment in a current of oxygen for like 10 minutes, and I observed how the scaffolds increase the amount of oxygen in the surface. I was breaking a bit the surface, and I got more CO bonds on the surface, which increased the hydrophilicity. It was very easy to see because I put a drop of water, and then it was before it wasn't go through, and now it penetrates inside the scaffold. So I checked the mechanical properties because this treatment is a bit aggressive and it actually decreased the mechanical properties of the scaffold, but we were still in the range of the tissue, so we were happy. And now we had like a better scaffold and more friendly for the body. Well, then I moved to the biological part. As I said, we do quite a lot of different disciplines here. And now I'm gonna ask you to think again. If you think, imagine we have cells, we see them on the scaffold, what are they gonna do? They will probably go through because it's a porous scaffold. I need them to attach to the scaffold and grow. If I just place them on top of the scaffold, they're not gonna attach or not that easily. Well, we have the opportunity to fabricate spheroids. Spheroids has another advantage. Well, they just literally little balls of cells. So we put a lot of cells together in a special kind of well plate, and they just form like spheroids that are made of many cells, a lot. If you use one of them, you're putting in just one of them a lot of cells. And I really need for such a big construct, I really need to have a lot of cells inside. To make sure the cells were alive after making the spheroids, I just did a small check in the confocal microscopy. It's just I labeled the cells, the live cells were labeled in green, and the diet one was labeled in red. And we see how inside one day I have like a lot of live cells. And then after 10 days, I left them in a plate and they started to expand. And I observed how a lot of live cells were expanded, and inside the spheroids we could find a few dead cells, which is something very expected because they couldn't get enough food to grow and survive. But I had a problem. Imagine I put the spheroid and then it goes through the scaffold. It doesn't attach. Well, I use gelatin, metacroyl gelatin that I cross-link with a photoinitiator for just 2 minutes and inject it. I put the spheroids in the gel mat, I inject it in the scaffold, and I just put just 2 minutes under UV light. Then this gel cross-linked, and I got the spheroid in the scaffold. How do I know that? Well, I took some pictures again. After 1 day, I injected the gel mat in the scaffold, and I saw some scaffold around the structure. Then, after 4 days, the spheroid started to grow. They start to develop, and they started to grow following the structure of our skeleton, which is important because I want to keep this structure to maintain and to have the ligament function. Then I did some, this is a Lamar blue. I checked just the metabolic activity with by UV spectroscopy. And then I checked how I needed at least a number of spheroid to have a proper colonization. I need a lot of cells to have this scaffold cover of cells. That's why the use of spheroids is very interesting. Here, I took some more pictures just to make everything more beautiful. And in this case, I stained the nuclei in blue and the cytoskeleton of the cells in red. We had this spheroids at the beginning, like in this little spheres structure, and then they were growing, and they were growing through the structure of the scaffold. We saw that after 14 and 21 days, the cells were colonizing not only the structure of the scaffold, the fibers of the scaffold, but also they were connecting between them, between the struts, in the middle of the struts. As this project was very ambitious, and we got actually a lot of money to do this, we got a collaborator in Western Australia, in the University of Western Australia. I was very lucky to have them because I learned something new that I didn't know at the moment. If you train the cells, they can orientate. It's like when you put your cells under mechanical pressure, they can organize themselves. And this is very usual in ligament and in tendon. And if you have your cells organized and you put them through a concrete mechanical stimulation, you can align them. And the alignment of the cells is going to be very important in terms of recover the structure of the tissue. Here we have the bioreactor. We just put some scaffolds there, and we were just stimulating them with a mechanical stimulant, just doing literally this for 1 week in cycles. And then we also, after checking that, we check what is going on with those cells. We didn't have much time to finalize this study, but we check how some proteins increase after this stimulation. Some proteins that are really related with the cell differentiation. In this case, it was very interesting. And in this case, we also checked the mechanical properties before and after this mechanical stimulus, and we found that we didn't observe many changes. So we observed an increase in the tenomodulin and collagen 1 hit the same after all this stimulation. Now that we've been speaking a lot about this concrete case, I just want to show you a bit as a conclusion that bone ligament bond, this UV safe scaffold was manufactured with PET, was interesting for the reconstruction of this ligament, and it has interesting mechanical properties. And we have, with the inclusion of the spheroid, created a construct that has a lot of potential to recover this tissue. Now, I'm gonna release you another question. I'm asking a lot. And think just for 1 minute, because we're gonna change completely the topic. We were speaking about ligament, now we're gonna speak about bone. How many people do you know that need a bone replacement? Just thinking right now, my two grandmas, she has 2 knees of titanium, and well, with the aging, many people need things. We don't have to go that far. Like many people have implant in the mouth because of a defect, or some bone can be damaged in the jaw, but it's very usual. And even more close to us, we have some toothpaste that have something to regenerate the dentine of the bone, of the teeth, because it also degrades. So this is also an interesting market, and this is a very general one. Bone, it has a very special structure. I'm gonna explain it to you right now. Well, as I mentioned before, when most of the chemists start in bone, starting tissue engineering because of the bone, because this is a composite. It's an inorganic material, it's nanocrystalline hydroxyapatite, and in combination with type 1 collagen. So most of us started to work in this to creating new materials for bone regeneration, most of them new kind of biomaterials. But bone is not that easy. Compared to other tissues, we have a huge structure and a huge balance in our body right now. So we have 2 kinds of cells, osteoclasts that are, they have to resorb the bone. So they are able to dissolve the hydroxyapatite and the collagen and create legs, just create holes during the bone. Then we have other cells that are in contact with the osteoclasts, and they are the osteoblasts. They create the bone. You may think, why do we need to resolve the bone? Why do we want to destroy bone? Well, we have to grow, and we have to grow with an order. The bone cannot grow whatever. We need an order, and osteoclasts are responsible of that. The problem here in the bone is when you have osteoporosis is because the communication, because those two are not good enough. And osteoclasts start working like crazy, and osteoblasts are not working properly to regenerate all the bone. But for now, we are all healthy. So for now, this is working properly. I just gonna show you a picture that I took in the lab of an osteoclast. You see how big is this cell with a few nucleus, and this creates, they can literally dissolve the surface of a bone. You see, this is a surface of a bone, and this is, we call it osteoclast lake, which is they release acid and a key catepsin, and then they are able to resolve the bone, dissolve it literally. We have, on the other hand, the osteoblast. You see how they much smaller, and they grow very, very fast to regenerate the bone. They are able to mineralize, to release calcium phosphate to the media and create the bone. Well, now that we know a bit of the bone, I want to speak about third generation of bioceramic, completely bioactive glasses. I really like those materials. I did my PhD on those materials, and they have, compared to other materials that we use for bone replacement, like, for example, metallic prostheses or hydroxyapatite itself, those materials have the ability to regenerate the bone. They are bioactive. So what is bioactivity? The bioactivity is the ability of the materials to bind to live tissues through a mechanical, strong, and chemically stable bond. There are a lot of biocompatible materials, but there are not many bioactive materials. It's not that easy to find a material that can actually form a strong bond with our live tissues. How is bioactivity working? This is mostly, this is for bone in a case of a bioactive glass in contact with a live tissue. So we have the bioactive glass. We put our glass in contact with for example, plasma with a biological solution, and then they start to create a hydroxyapatite layer on the surface. Here it's happening because there is an exchange of calcium with the media, and then it's like amorphous calcium phosphate precipitate, and then it's involved into a hydroxyapatite-like, which is the same mineral that we have in our body. That's why they can bond strongly, because they're literally the same. Then our osteoblasts will come and will colonize the surface, because they will recognize the hydroxyapatite, and then we will be able to create new bone. This is very ideal, and of course those materials are not yet, are very far from regenerate a big defect. For example, they cannot be used, their glasses, they're not that strong. They cannot be used for a big defect, but for example, in terms of dentistry, they have a lot of application. Well, it's important to mention 1991, that year, because in the same year they discovered the sol-gel glasses that were just synthesized by sol-gel chemistry. They put the precursors after hydrolysis, condensation, and aging. We got a glass like that is made of a silicon structure with some calcium phosphate embedded in during the network. And then in the same year, they discovered the mesoporous silica material by the Mobile Oil Company. This just combined the surfactant chemistry with the precursor chemistry to make bioglasses, and then we created mesoporous silica. They created mesoporous silica materials, which have some specification. Well, now combining both bioactive glasses, sol-gel glasses, and mesoporous synthesis, like the creation of mesoporous silica materials, and the evaporation-induced self-assembly method, combining all this expertise, we were able to create multi-component material that are also porous. So this is where we started to prepare mesoporous bioactive glasses. So using just a volatile solvent, adding the precursor and as a structure director agent, a surfactant, waiting for the matter to organize, we get the final structure. Here we have a control in the composition, which are like mainly silica, then calcium oxide and phosphate, or oxide phosphate, that are gonna be able to start the apatite nucleation, and then we can also control the structure. We can control the mesoporosity of the material, and this is gonna be is gonna have a very high specific surface, which will allow a faster ion release with the media, and then we will be able to enhance osteoblast activity, and in case of an osteoporosis case, decrease osteoblast activity, which will be interesting in terms of bone regeneration, even in osteoporotic cases. Well, here I showed you before two different kind of 3D printer. The cheap one was the one that I was using for the ligament, but I cannot do what I was doing during my PhD with that printer. I need something that allows me to print composite. So rapid prototyping or robocasting allows the printing of reproducible structures layer by layer with high porosity, and I was able to incorporate MBGs, my mesoporous bioactive glasses, in the caprolactome. Here you observe how I created porosity structures with like about 1 millimeter pore size to allow the cells to grow through. Here we did some experiment and we observed how cells were growing on the, you see here different areas. The ones that are raw, they don't have cells, but those kind of soft parts are just cells on top of the scaffold. We went to the confocal microscopy and we observed how we have some cells colonizing the surface of the scaffold. So they allow and they promote the colonization, the material promote the colonization of the scaffold by osteoblasts. And finally, we did some in vivo studies just to check how good are those materials, because we have our focus, which is to improve and regenerate the bone. So what we used a sick model which is a big animal. It's a mechanically competent model that reproduces osteoporosis in human. And we implant the scaffold, and after 2 weeks, we check what was going on there. So you see here the structure of the scaffold, but you see how a lot of parts are resorbed. And you see here in dark pink those areas that are new form bone. We analyze closer these areas and we observe active osteoclasts, active osteoblasts, some osteoclasts maintaining the balance of the growth tissue, and even blood vessels through the structure, which means that our material were very promising. We obtaining about 25% of bone regeneration after 2 weeks. So this is giving, like, those scaffolds were very interesting to regenerate the bone, and this rapid prototyping technique is very interesting to use to prepare those kind of constructs. And of course, the mesoporous bioactive glass has a lot of activity in terms of regeneration, helping the migration and the cell colonization in the constructs. Just, I want you to take home how fun is tissue engineering, and that you can, like, tissue regeneration, tissue engineering is combining of lots of fields, a lot of expertise, and we can somehow play and creating new constructs that combine cells, materials. We can play with the structure, and we can even add drugs or other bioactive molecules to stimulate the tissue regeneration. And now, thank you for your attention and for inviting me again. And if you have any question, I'm very happy to share, to discuss anything with you.
too much. Do you have any questions?
Thank you for the talk. Very nice. I'd like to ask you about the ligament part.
Yeah.
When you talk that the ligament is fine, has some anchors that go into the bone.
Yeah.
Can you explain a little bit
Yeah.
more how to
Yeah.
do that thing?
Yeah. It's here. It's
Yeah.
so. The problem with the ligament and when it's interosseous is because the ligament is literally growing from the bone, right? So to recreate this kind of defects is very, very complicated. So we needed something to put the ligament reconstruction, but we didn't have any anchor to put like just just the new tissue, just the scaffold. That's why with the surgeon, he recommended us to just think of creating, here I have, just creating 2 little holes in the bone. You insert the bone plugs and then just grow. Something that could have been very interesting, it was, it was my initial idea, but time flies and you don't have time to do everything. It was to introduce in the bone plugs some of these bioactive glasses to check how, like, to create also bone in these areas, and then to have a proper construct bone, ligament bone construct. But the idea was, yeah, just to insert like those bone plugs inside the bone. That's why you need the surgery, and this the surgeon will have placed a couple of holes in one each, and it was the initial idea. I don't know if this was your question.
Yeah. Yeah. I guess that is the weakest point of the ligament.
Yes,
Because the strength of the ligament itself looks quite convincing, but perhaps that
Well, I didn't put that in because I don't want you to feel disgusted, but because it's when you work with clinicians, you realize that you have to have a bigger stomach. So we had we literally put this in arms of dead people. They donate their arms for the research, and we working with a different guy, Alistair. He created like a robotic arm. So we placed, imagine, I cut my hand, like literally I cut my arm. We place that in the machine. The surgeon places the scaffold, and we started to do all the mechanical like movement. And we show that was the main problem. Like some scaffold, if the bone wasn't good enough, some scaffold just flew. That they just drop and just jump from the actual construct. So this is the main, and that would be the main problem actually, because in terms of mechanical properties, it was good, but in terms of the anchoring to the bone, it was the weakest point. Yeah.
Yeah, my second question has to do with the test that you have made in actually real bone and real parts of the body. Are all done in dead bodies, or
Yeah.
you have worked also with in vivo parts?
So there is we have worked just with death. For now, it's just, so we haven't checked, and this is a good question because we haven't checked the regeneration in vivo. We have checked the biocompatibility in vivo because we put those scaffolds, not exactly those ones, with a bit of a different composition in rats, just to check that they weren't increasing the immunoresponse, that the body wasn't rejecting the construct. But in terms of using this in alive patients, we haven't done that because we need to go through many different paperwork, and to take those to the clinics is very complicated, and we're really far from it. This is a patent that they had before I arrived to the lab, because they had the idea of the UV structure just before I arrived. And this is protected, and they're speaking with some companies, but we are far from that. The surgeon was really happy though, and he wanted to start trying because I guess he sees the people suffering. So he was like, okay, let's try. This is not gonna kill you, but yeah, it has to go to many things. We have just doing this trial with all, like with dead people.
how do you take into account the body reaction? Because you mentioned before the porosity.
Yeah.
There are other parameters that you check in the.
Yeah, sure. With this, I love this project, but you know, you arrive to a new place and then you come back and I wanted to do many more things because when we check the body reaction of anything, first of all, you check in immuno cells. So usually we check macrophages to check if they're gonna polarize to regenerative phenotype. This means that if you have the macrophages, they accept the construct, it looks like it's gonna be happy. This will be in vitro. Then in vivo, we do some studies, and when we have a very big inflammatory response, you see it because it's just so that will be what we have to do. We haven't done it, but for those scaffolds didn't have an inflammatory response, which was good. Just this small study with the rats, but you have to go for like longer times because the rejection sometimes happen with the time. It's very usual when you put an implant. Not that usual in the knees, for example, but with the for like the mammary implants, they get rejected very often because it's a plastic in the body, so it's gonna encapsulate the body, the strange body that you're implementing, and then you will see how creates an inflammation, and you have you see the increase in the level of immune cells. Yeah, you have this kind of inflammation.
And about the mechanical properties that you plotted.
Yeah.
What are the most important mechanical properties you have studied in order to check the
It is the thickness.
stiffness?
Yeah, because we need it to be flexible, and it's not compared to, for example, the knee that it needs to have a lot of load, like it's always tolerating our weight. Here is not gonna be like that. If you can say a patient, don't just lift heavy weights and you can still going, but if the stiffness is not good enough, it can break easily. So it's the most important one because here you can still move the hand and it should be fine. Yeah.
Okay.
I have a question on, well, first, thanks for the talk, it was very interesting. And I have a question on the porous structure. Which are the parameters that you must find that you have to optimize, because I imagine there are some porous that are worse and other structures that are better.
Yeah, that's a good question. It takes, I mean, at some point in the lab, you have to choose one thing and go, because otherwise it will be crazy. We found that this amount of porosity was good enough, and that's why we went through this. Because, for example, everything is very well think here because we have 7 struts, and if we had like in 5 millimeters, right? If we had 8 struts, it was too thick. So we couldn't, like the mechanical properties, the flexibility was much lower and it wasn't as good. And if we had just 6, it was too soft. So 7 was the optimized results, is what we were doing. So we, in terms of these 7 struts that we have in the ligament part, we did a few studies with the help of Natalia of the simulation. She helped a lot. And then that's why we have here this porosity. And in terms of layer, we got this because this ligament concretely is very thick. But for example, I've been working with other kind of, for the regeneration of periodontal ligaments, and those fibers are super, super, super thin. They're about micrometers. So this is, you have to optimize for your application. So in this case, I think it was a good approach and it was based on the simulation maybe. But yeah, it's because like we got this nozzle because we did some trials, and we did some trials printing with a nozzle of a very, of a smaller, it was a smaller nozzle. The diameter was 0, this is 0.4 and the other was 0.2. And again, the mechanical properties weren't as good. So you have to, I was all the time doing the mechanical studies and coming back to the lab. And also this is with a lot of repetition. You have to, it's quite a lot. But yeah, that's why we choose this. More than 50% of porosity is good. in terms of tissue regeneration. Yeah.
The interplanar distance also affects a lot to the cell grow, or
It does, and in this case, we have chosen this separation because in the simulation was also the best one. We tried, you see here, we could have done more here, but it wouldn't have been that good in terms of mechanical. It was too thick and it breaks more. So that was the optimal conditions. Yeah. Thank you.
How do you run these simulations? Do you put two courses in the course with the?
Yeah, the simulation, Natalia did it mainly, the collaborator, but I think at some point she started with 2 point, and then she even went to a first one. I am not sure, but yeah, it was like two forces, opposite
Do
forces.
you take into account the natural movement of the?
Yeah. Yeah, actually, it's part of the work that is gonna be published with all the cadaveric tests that we've done. Yeah, they haven't published it yet, but yeah, they did then, after the simulation of the structure, they did the simulation inside the bone with all the cadaveric tests. It was a big work, like they were very smart actually. But yeah, I wasn't part of that anymore, but it's something you have to check, definitely.
Do you have any other question? Well, let's then again, Natividad for this great, okay, thank you so much.
Thank you.